Noble gases, the elements in group 8A, so helium, neon, argon, etc. here, are exceptionally stable. They're noble. They don't deal or react with all those other peasant elements, the representative elements. Noble gases are stable because they have entirely filled valence shells. As an example, neon, you can see that its electron configuration is 1s2, 2s2, 2p6. You can see that principal energy level 2 has all of the 2s subshell and all of the 2p subshell filled. We can say that neon is very stable. It has a full octet. It has, let's see, 2 plus 8. It has 8 valence electrons, electrons in the outermost sublevels in the outermost principal energy level that is filled at all. Now, neon is very stable. It has a filled valence shell. Fluorine, though, right next to it here, it is not as stable. It has only, let's see, 2 electrons in the 2s and 5 in the 2p. It has a total of 2 plus 5, 7 valence electrons. It is not filled. There could yet be another electron that could fit into the 2p subshell. Similarly, sodium, shown here, is also not stable because it also does not have a filled valence shell. There's only the 3s partially filled, and there's definitely no electrons in the 3p. So you would need 7 more electrons to fill that valence shell, principal energy level 3. Now, being that fluorine and sodium are unstable, they are quite reactive. In fact, when near each other, they will tend to react. You see, fluorine, if it were to gain just 1 more electron, it would have just as many electrons as neon. And instead of having 5 electrons in the 2p, it would have 6 electrons in the 2p, just like neon. It would have a filled valence shell, a full octet. So fluorine, it would become more stable if it were to accept 1 more electron, and sodium, if it were to lose this electron in the 3s subshell, then it would have just electrons in the principal energy level 1 and 2. It would have 2 plus 6, 8 valence electrons in that principal energy level 2. Principal energy level 2 would be filled. Sodium would also have the same electron configuration as neon if it were to lose that 1 electron in the 3s subshell. And so sodium, it will become more stable to lose this electron, and fluorine, it will become more stable to gain an electron, and so sodium will send an electron over. It will send this electron from the 3s subshell to fluorine's 2p subshell. Another way to draw this is in using these Lewis dot structures, where each of these dots represents the number of valence electrons around each of these elements. We can see that neon has 2 plus 6, 8 valence electrons, 2, 4, 6, 8, a full octet. Fluorine has 2 plus 5, 7 valence electrons. It would like to have 1 more. And sodium has just that electron in the 3s subshell, 1 valence electron. If it were to lose that 1, then underneath principal energy level 3 would be principal energy level 2, which would also be filled. We can show that sodium would lose this 1 electron and fluorine would accept it, so that there would be these new electron configurations where fluorine now having 1 more electron is 1s2, 2s2, 2p6. The s and p subshells are filled, full octet, same as electron configuration as neon. It has a noble gas configuration, stable. Also now, sodium, having lost that 3s1 electron, it has just electrons in principal energy level 1 and 2. There are 2 plus 6, 8 valence electrons here, full octet, stable, the same as neon. So we can see that both fluorine, when it gains an electron, and sodium, when it loses an electron, become more stable, become just like neon. And so they have these new electron configurations. Fluorine gained that one more electron. It looks just like neon here. And sodium, though we don't draw it, it also has now 8 valence electrons too. Now, when fluorine gained that extra electron, that affected its overall charge. Originally had a charge of 0 because fluorine had, being here it had 9 protons, and being an atom it had 9 electrons. It had just as many protons as electrons. But when it gained one more electron, to be just like neon, to have 10 electrons, it had 10 electrons but only 9 protons. It had 10 negative charges and 9 positive charges. It had one more negative than positive charge, and therefore it had an overall negative charge now. F minus was the new designation for this. So we now call it fluoride. Monoatomic anions end in "ide." And similarly, sodium, it originally had yes, sodium has 11 protons and 11 electrons originally. But after it loses that electron, it now has 11 protons and only 10 electrons. It has one more positive charge than its negative charge, and so it is called Na+. So you see that if you gain electrons, you have a negatively charged ion formed, and if an atom loses electrons, it gets a positive charge. Now, negative and positive charged ions have different names. Now, an anion, fluoride as an example, is a negatively charged ion. And a cation, sodium ion as an example, is a positively charged ion. These are easy to remember if you remember that cat ion. You see the T here? That almost looks like a positive charge. So cation with the big T, that's positive. Now, you are able to predict the charges of other elements as well. We had seen that sodium turned into +1, and fluorine turned into fluoride F-1. Similarly, potassium, if it becomes charged, it will get a +1 charge just like sodium. And chlorine, if it becomes charged, it will get a -1 charge just like fluoride. We can see this because chlorine is just like fluorine. You see, they both end in P5. We can see that they're in the same group. Fluorine and chlorine, ending in P5, they can both accept one more electron to be just like the most nearby noble gas, neon and argon. And so they both will accept one electron and get a -1 charge. And sodium and potassium will, they both end in S1. They'll both lose one electron to be just like the most nearby noble gas. And so they'll both get +1 charges. But what about elements in group 2A? They end in S2 to get a noble gas configuration. For example, for magnesium, to get a noble gas configuration and be just like neon, we need to lose 2 electrons to be just like neon. It would therefore get a 2+ charge. Aluminum, here, it would lose 3 electrons, 1, 2, 3, to be just like neon. It has 13 electrons, and to be just like neon, which has 10, it needs to lose 3 electrons, so it will get a +3 charge. Then we can go and see oxygen and sulfur. They both can gain 1, 2 electrons to have noble gas configurations. If they're ions, they have -2 charge. And nitrogen and phosphorus, they'll gain 3 electrons, 1, 2, 3, to be just like noble gases. Gaining 3 electrons, they'll get -3 charges. So we can predict what charges there are on certain monoatomic ions by the place on the periodic table. You should memorize that the metals here, and then the transition metals, and then also aluminum, they get positive charges, positive 1, positive 2, positive 3. And the nonmetals, they get negative charges, negative 1, negative 2, negative 3, because they gain electrons from metals. Of course, though, neon, helium, etc., the noble gases don't get charges because they are already stable. And transition metals, they have a complex way of losing electrons, which we won't need to cover. Although we will later recognize that certain elements, like copper, get certain charges like positive 1 and positive 2. Zinc always gets positive 2 if it's charged. Silver always gets positive 1. Cobalt is plus 2 or plus 3. We also have iron, which is plus 2 or plus 3. So you'll have to sometimes figure out those charges using a little bit of algebra, which we'll discuss later. Thanks for watching, guys.